Introduction overview. So for today and tomorrow, it's all the same stuff. It's introduction overview of today and tomorrow. I like to see the big picture sometimes, like, okay, how does this all work together before we get into the individual topics and details is nice for me. So just definition of neuroscience. It's kind of a relatively new science. It's concerned with development, chemistry, structure, function, pathology of the nervous system. So it's a very integrated type of science. And as we've gotten better tools, imaging, different types of electrical ability to assess electrical activity, technology has allowed us to have a much more integrative and better understanding of neuroscience. We're still so far from understanding much of anything about the brain. It's crazy, okay? You can kind of specialize in different areas. There's different types of neuroscience. Molecular, so at the molecular level, the cellular level, the systems level, autonomic nervous system, sensory, motor, those kind of things. Behavioral. I wish I knew more about the behavioral neuroscience. That fascinates me. And you'll find that same thing when you're out in the clinic. You'll wish you knew more about behavior, psychology, those kind of things, because I always feel like I'm kind of limited in that way working with patients. Cognitive, same thing there. I really think that's so neat is the cognitive aspects, and I wish I had more time to kind of get into that. We're going to do physical therapy or clinical neuroscience focused, okay? So we're looking at a more integrative clinical, how does the nervous system, how does deficits or impact or function of the nervous system relate to us as a clinician, and how we treat patients is what we're going to be focusing on, or trying to anyway. That doesn't mean we're not going to cover aspects of those other parts of neuroscience. We're going to look a little bit at cellular and developmental overview, okay? We're going to look at the major functional systems of the nervous system, okay? We're going to look at then a regional look at the nervous system, brain, spinal cord, brainstem, those kind of things. Then we're going to go into special functions, okay? Vision, vestibular, okay? Then we're going to go into support systems like the meninges and the blood supply, okay? So if you look at your schedule, they're kind of organized by those topics. So you see we have structural, cellular, developmental overviews for the first few lectures here, and then we have an exam next Friday, right? That first exam comes so quickly. So next Friday, but we take it in smaller chunks. One of the things I got from feedback is like, it's better to give this in a little smaller chunks. I used to only have like two exams. Then I went to 3. Now I'm up to 4 exams, and I think people do better with that. They appreciate that, and the lots of quizzing and smaller chunks gives you more opportunity to redeem yourself too, as you go through that. People do well in that first exam as long as you're staying up and doing the work. Okay. Now, a couple interesting facts. About 3 pounds is what your brain weighs. About 2% of our body weight. So our brains are relatively big compared to our body weight. Elephants have much larger brains, but as a percentage of their body weight, it's much smaller. I think this next one is kind of very interesting. 100 billion neurons is what we have in our nervous system. And if you laid them side by side, not end to end, you took all those neurons, just laid them side by side, it would actually go 600 miles if you laid those all out. So amazing that can all be compacted into our nervous system. Over 1 quadrillion connection points or synapses. So you think about just the incredible complexity and integration that's going on with all those synapses. And the cool part about us as physical therapists is we can change those. We affect those synapses, and we can do specific things to make those change to help a patient. And that's what the cool new research and the new scanning techniques and imaging techniques are showing, is that we change brains. We change muscle function, but we change people's brains. So that's pretty cool. You've heard that thing about using 10% of your brain. We only ever use 10% of our brain at a time. It's not really. It's kind of a myth. We do use, most of our brain is working at any one given time. Your attention may be directed to certain things or certain activities, but your brain is still functioning. Sometimes I feel like I can only use 10% of my brain. There's certain days where it's just like I can't even get a complete sentence out. But we do use most of our brain. This is my son, Mitchell. These are a few years old, these pictures now. He's a junior in high school right now. Junior, yes, he's a junior. He does a little bit of music. He's a trombonist. Jamie, do you play? What do you play? Saxophone. So he does like that. trying to get him to play in the pep band when he comes here so he can get to go to basketball games and all that stuff. He's not too thrilled with that idea yet, but we'll see. He likes travel. My kids are crazy. They like to go out and do adventurous stuff. So this is him in Peru on kind of a mission trip, getting ready to lay concrete floors in 90-degree jungle humidity. I like that picture, just nice and dirty. And he's actually a pretty hard worker. I was worried about him. I thought this kid is going to be so soft. He's not going to do anything. Only when I tell him to do stuff hard, he won't do it. Anybody else tells him to go do something crazy and hard, yeah, I'll do it. He works at the school doing maintenance and all that stuff. But he'll do all kinds of crazy stuff for the maintenance director. But will he go out and change his oil in his car or do his brakes? No. My daughter's different. She'll actually do that stuff. But and then he went to China with a friend. He's got a friend who's from China, an international student, so he took advantage of that and went out there. And he stayed there for a couple of weeks in Beijing with his friend. And the same friend's parents now moved to Australia, so guess what he's doing for spring break? He's going to Australia for 2 weeks, so hence I didn't go anywhere over Christmas break. All my kids go everywhere, all over the world, so my wife and I stay home and help them do that, so crazy. So he's telling me, he's been on 6 continents. By the time he's 17 years old, he's already been on 6 continents. He just needs to make it to Antarctica, so crazy. All right, components, organization of the nervous system. This is big picture, okay? So we're going to look big picture here on the major parts of the nervous system. I'm going to assume this course, I assume you know nothing about neuro. Because if you've probably forgotten what you did learn, and with last semester your brain's so scrambled you can't remember anyway, so we're going to put you all on the same level playing field, that you know nothing about neuroscience, and start from the very basics, okay? I like to visualize things, so on the back of your handout there, should be on the back side of this, I think, somewhere, or last page, should be a little sheet like this. And this is just sometimes I go back and go, all right, what's part of what? How do these parts of the nervous system all relate to each other? So this can be helpful. Let's see if I got a new computer too, so let's see if my little drawing thing works here. Here we go. Yeah, so you start here, nervous system, right? We can look at different parts of the nervous system. So we have just the basic neurons and neuroglial cells, okay? Basic division there of just the basic neurons that make it up. We have an autonomic nervous system that has a sympathetic and parasympathetic component, okay, which we'll talk about in a few weeks. We have our peripheral nervous system, which you've done a lot of work with. You've mainly done all your work here, spinal nerves, okay? So you've already know about the spinal nerves and the peripheral nerves that go to the muscles and supply your muscular system, okay? But we're going to talk also about cranial nerves. Cranial nerves are just like spinal nerves. They just tend to come from your brainstem and your brain, okay, and your sacrum. They do some of them come from your, the cranial nerves come from your brain and brainstem, but you also have some sacral nerves that are also spinal nerves that are part of the craniosacral autonomic system. Then we have our central nervous system, and then you start moving out from the central nervous system. You have a brain, right? That brain can be kind of divided into, the brain consists of the cerebrum, which we think of as like, when you think of a brain, you usually think of the cerebrum, this kind of part right up here, okay? You have the cerebellum, which sits just below the cerebrum, and then you have the brain stem. Those are all considered part of the brain, okay? And then I'm not going to go and follow all these out because we're going to get into these, but you can see how you can just go and further subdivide each of these into major areas. And you can keep going from here. I just kind of stopped at a point that makes sense from the major components of the nervous system. So sometimes when you're going on individual slides, and you can kind of have this sitting here like, where are we at here and what part of this is what? So that's what this is, just to help you kind of have a quick one-page picture of the nervous system, major components and subdivisions. So we're going to go through these basic components. We're going to start with neurons and neuroglial cells. This is like the really quick overview of today. We'll do more in-depth on Friday with some of the neurons and neuroglial cells and get more specific in how they communicate and action potentials and all that stuff. We'll talk about central nervous system today real quick, the peripheral nervous system overview, and autonomic nervous system overview. The autonomic nervous system, it has parts of it are both in the central and peripheral nervous system. So this is somewhat of an artificial division, but it is I try to stick to mostly what your book says, so we have a consistent kind of theme going here. And speaking of your books, I don't know if you noticed on your schedule, I give you, readings, whether it's out of this book here, this, what, third edition of Lundy Eckman here, or this fourth edition here, the larger book. I like this format. It's a little easier to use and read. This book's okay. It's about as good as you can get for a rehab-specific neuroscience book, okay? This book here, I love this book. This is the book that would sit on my shelf in the PT clinic, probably even more so than this book. This is more of a neuroanatomy focus, but it's just very well done. And it's got some really nice, and we'll get to that, we'll talk about some of these really nice graphical things and tables that are very clinically focused of, what kind of deficits you see if somebody has damage in certain tracks and pathways. And I find this a much quicker reference guide to me when I'm trying to figure something out with a patient. And this is just a nice, that's why I still like you guys to have this. It's just a great, and that's why part of the reason I kind of got rid of the lab manual is because this does a pretty good job here, and I just gave you the essential things that you might need for the lab manual. Okay. All right, where did I set? You guys have to keep track of my stuff, my little pen, I spend a lot of time searching for those things. So let's look at neurons first, just basic structural functional unit of the nervous system is this thing called a neuron. If your neuron conveys information towards the central nervous system, so you've got a peripheral nerve or neuron that's sending a signal towards your central nervous system, okay, like a sensory nerve, those nerves are just basically like one long neuron. They have an axon that projects all the way down to your foot and all the way up towards your spinal cord and sends that signal towards the central nervous system. That's going to be called an afferent neuron. And I think of the A in afferent as acquire. Acquire. I'm acquiring information. Information is being acquired or coming into a structure. It's not necessarily even that it's coming from the peripheral nervous system to the central nervous system. That's how we mostly think of it, especially as clinicians. We think of the sensory system. Any kind of sensory information, whether it's vision, vestibular, skin, muscle, spindles, joint receptors, any information coming in is afferent information that goes into the central nervous system to be processed. Okay, so an afferent neuron is one type of neuron. If you have a neuron that projects outwards or away from a structure towards another structure, most commonly from the central nervous system out to a peripheral structure, we typically call it efferent, an efferent neuron. And I think of the E as in exiting. It's exiting away, whatever you want to use. Trick works for you to help remember that. So efferent neurons take information away typically from the central nervous system towards muscles, towards glands, towards whatever, okay? If a neuron only connects with other neurons, which is most of our neurons, are called interneurons. Afferent neurons typically are connecting, so like the afferents typically have like a receptor, a specialized receptor that initiates that signal in that afferent neuron. So they're connecting with a specialized receptor. Efferent neurons are going out and connecting with an effector organ, whether it's a muscle or gland or something like that. But interneurons are only connecting with neurons. It's just a connection between two neurons. And that's where a lot of our hardcore processing goes on, is that integration at the interneuron level of giving us that kind of very dynamic, flexible nervous system that can integrate information and process it. So interneurons. And that's most actually, large we always think about those big afferent, efferent neurons that do the action or bring the information in, but it's the processing that inside the nervous system, that the interneurons, it really is the critical part of that. So that's the neuron, okay? They're excitable. They can have action potentials. They can change polarity, okay? The other major class of neuronal cells are called the neuroglial cells, okay? So the neuroglial cells, and glial literally means glue. And it's like the glue that holds all the neurons together, okay? It provides substance, but it's the support cells, okay? It's this, holds everything together. It insulates, it provides some insulation. Some of the glial cells that make up our meninges and our coverings help kind of insulate the nervous system. They make the Schwann cells that kind of wrap around the axons to like insulating a wire. That they create the insulation. They provide nourishment, okay? They have some ability to nourish the cells around them. They also help get rid of some of the waste products of metabolism around it. They help to protect, okay? So they provide some protection to the neuron cells. This is an astrocyte here that you're seeing. It's called an astrocyte with some little end feet. Those little end feet kind of project and support neurons, and also even support and wrap around some blood vessels for the blood-brain barrier, okay? So that's an astrocyte. Neuroglial cells repair themselves and divide, even into adulthood. Neurons, much less so, okay? So the neurons themselves don't do a lot of. Now the new research is showing they probably do more reproducing and than we used to think. You always probably used to hear that once you lose your brain cells, you'll never get them back. There is some ability for neurons to repair themselves and continue into later life to regenerate, but neuroglial cells are much, much better at that. They can repair themselves and continue to divide and regenerate, yeah.
Is neuroglial and glial synonymous?
Yes. Glial cells or neuroglia or neuroglial cells or glial cells are the same. Okay. Yes. Yep. So glial cells. Yep. You've heard of like a glioblastoma, so that's a common, of course, brain cancer. Okay, so that's glioblastoma, glial cells that have gone haywire and overproducing and overdividing because they do divide, but that can be a problem if they aren't able to check themselves. This is my daughter. A lot of you may have seen my daughter walking around here. She does some of the cleaning in here. I don't know if you've run into her. She's got a shorter hair now, but this is her non-glamour shot, and then her glamour shot. That's actually that's her senior year in high school. So her name's Abby. Well, it's actually Gabrielle. Went from Gabrielle to Gabby to Abby. So, but that's what just goes kind of. She's a sophomore here now. I can't believe she's a sophomore. She's actually on her first co-op. She started last week she's engineering. She goes, I don't want to work with people. God, people are so complicated, so messy to work with. She goes, I just want to work with like things and objects and so forth. So, but she's finding out, as an engineer, you still got to work with people. It's still all about teams. You can't do it in isolation. So she's working at a place like a metal forming place here that does auto part stuff. So but she seems to be fitting in. I think she's one of the few females in the place. So she kind of feels like everybody's eyes are on her a little bit. But yeah, so I had her home for the break, so that was kind of nice. But she's back on campus. She doesn't, once you leave home, it's hard to come back. It just changes the whole dynamic. So I'm okay with her she's living with her roommates again on campus. So enjoying that, and I'm happy to have her do that. So, all right, a couple more minutes here, and we'll take a break. So that was the neurons and neuroglial cells. All right, very just super quick, introduction. Now we're going to talk about the central nervous system and its major parts, which are on that sheet, that outline. That's all we're covering right now, some of those major parts. This is what your book says, and most books talk about is the 7 main parts of the central nervous system. You've got your cerebral hemispheres, which includes these inside the cerebral hemispheres, nice and deep inside of these things called basal nuclei or basal ganglia. Ganglia and nuclei are very, interchangeable, okay? Those terms. So these are some cell bodies, groups of cell bodies that are down deep inside the cerebral hemispheres, and we'll get to those way later, okay? You also have a thing called the diencephalon, okay? The diencephalon, encephalon, it's inside your cephalic area. The cephalon is kind of your brain, basically, the cerebral hemispheres. It's within those, is the thalamus and hypothalamus. So again, this is a deep nuclear structure. These are structures that are mostly cell bodies that are deep nuclear structures within, kind of in the cerebral hemispheres, but they do separate this diencephalon out as a major part of the central nervous system. It's a relay structure, this diencephalon, okay? And I think we'll talk about it in a few minutes here. Then you keep working your way down, okay? We're kind of starting at the top and working our way down. Then you get to what's called the midbrain, which is part of the brainstem, okay? But it's right up kind of in the middle of the brain in a sense. It sticks up kind of inside there, okay? And then sitting back off the back of the brainstem is a thing called the pons, okay? Well, the next below, not behind, that's cerebellum, but just below the midbrain, the next structure in the brainstem is the pons. It actually kind of has a bulbous front part to it, the basilar part of the pons, we call it. Then we have sitting back behind the pons is the cerebellum, okay, which is not part of the brainstem. It's part of the brain, but it sits off the back of the brainstem, just behind the pons, called the cerebellum. And then below that is the medulla, which is part of the brainstem. We'll get a picture here in a second. And then from the medulla, spinal cord. Okay, those are the 7 main parts of the central nervous system. So here they are. All this structure area here, that's the cerebral hemisphere. And what we're looking at right here, this is a sagittal section right here. So if I'm this person here, I've cut right down through the center of my body. We're actually looking at the medial surface of my right hemisphere. So we're looking at the inside medial surface of my right hemisphere with a slice right down the center of this, we call the cerebral longitudinal fissure, that division right there. We just sliced right down. We're looking at that medial surface. Does that make sense? And then this is the diencephalon right here, this pink area here, which is the thalamus right here, is the more egg-like structure. And you can kind of see this. When we look at the brains tomorrow, you'll kind of see the curvature there that kind of shows this division. And this area down here below is the hypothalamus, okay, below the thalamus, hypothalamus. Then here's our brainstem. So the brainstem is this whole area from here to here, okay? And it's divided into, there's our midbrain. And you can see this midbrain is kind of, when you look at where the cerebellum, the brain is kind of up in that middle of the brain almost, in a sense. And then here's the pons. Next structure in the brainstem is the pons. And then the medulla below it, but then here's the cerebellum sitting back behind mostly the pons. And then lastly, we have the spinal cord. So those are our 7 main parts of the central nervous system. Yeah.
The light yellow one that's pointed to, it's not labeled.
Oh yeah, that's not considered part of this. I mean, it is part of the central nervous system, but it's not one of the 7 main parts. But it's the corpus callosum, which we'll get to tomorrow. We'll be showing that. It's a connection between the 2 cerebral hemispheres. Commissural fiber between the 2 cerebral hemispheres. That's it, central nervous system. Sweet, we're done. Peripheral nervous system, what you guys have been studying all along. So we're not going to do a lot of peripheral nervous system stuff. You guys probably know your peripheral nerves better than I do right now as far as nerve roots and muscles and those things. Well, maybe you did a few weeks ago, but you did the full dump, before you got back. But so anyway, you can at least leave that for a little while. Have one up on me for a little bit till we get to the hard stuff here. So it's all the parts of the nervous system that are not encased in the skull and the vertebral column. As soon as you get out from the brainstem or the spinal cord, even though you're kind of still in this, you're within the spinal column for a brief moment before you get outside of it, as soon as you leave the central nervous system, you're in the peripheral nervous system. As soon as you exit that, those central nervous system structures, okay? And we're typically talking cranial nerves and spinal nerves, okay? We have 12 pairs of cranial nerves. We always have pairs of these things. Just like we have pairs of spinal nerves, they come out to both sides. They go to both sides of the body. You got to supply right and left the same, right? And so those are cranial nerves and 31 pairs of spinal nerves. So what you see in yellow there is your peripheral nervous system, okay? And what you see in that bluish gray or whatever that color that is, that's our central nervous system. And what I'm going to do on the quiz tomorrow is you'll just see this structure here, and you're just going to try to identify all those yellow things, those yellow nerves is all you have to, just to try to get as many of those as you can. I'm just kidding. You guys are freaking out. No. Autonomic nervous system. So the autonomic nervous system, it has parts of the autonomic nervous system are both in the central nervous system and the peripheral nervous system, okay? But it can be, these different parts are classified as 2 different major subdivisions. The sympathetic nervous system, okay, which is also called our fight or flight type of, it's the one that typically increases metabolism, increases activity of the body, awareness, vigilance, those kind of things, the fight or flight. It's also called the thoracolumbar division of the autonomic nervous system because the nerves for the sympathetic nervous system are coming out between the thoracal and lumbar areas, okay? So the sympathetic nervous system exits out, and they actually go out in the spinal nerves, okay? They're actually part of the spinal nerves. They just go to blood vessels and sweat glands and those kind of things to drive those functions, okay? That's the gut and the heart and all that stuff. So that's the sympathetic nervous system. Then the parasympathetic nervous system, also known as the need and feed, it tends to slow things down. It's important for lots of functions, digestion, slowing down heart rate, blood pressure, blood control, all kinds of things. So we'll get into all the details of that later. It's also known as the craniosacral division of the autonomic nervous system because the cranial nerves, there's a number of our cranial nerves, especially vagus nerve, cranial nerve number 10, does a lot of control, the parasympathetic control of our organs in our body, okay? But the parasympathetic signals come from the cranial nerves and also from a few sacral nerves. There's a few sacral nerves that carry, especially to bowel, bladder control and those kind of things. Parasympathetic control of that is driven by those sacral nerve roots. So that's what they call it, the craniosacral divisions. And then sandwiched in between, the sympathetic nerves come mainly out of the spinal nerves in the thoracolumbar area, but the parasympathetic nerves and control come from the cranial nerves and those sacral nerves, okay? And this is a little quick overview here that just shows you some of that going on there. So you look here on your left is the sympathetic nervous system. So you see it here. These are the nerves here exiting out. We'll worry about these little sympathetic chain ganglia later, but they go and drive sympathetic control from this, thoracolumbar area, okay? Whereas the parasympathetics are coming from, you see the cranial nerves, okay? This is cranial nerve 10 is driving a lot of what happens in the body. And then also some of the sacral nerves down here, okay? So this is more craniosacral division. Parasympathetic, okay? All right, looks like this is a good time to take a quick break before we get into some of the language. So let's come back. It's 9:52. Let's be back in 10 minutes, so 2 after 10 o'clock or right around that time, so close to 10. All right, so I think it's important if you kind of, the hardest thing about neuro is kind of with the language, is learning kind of terminology. I hope I can help you kind of, if you kind of know there's certain key elements to how some of these words are put together, it helps you understand how the tracks are arranged and where they're coming and going from and those kind of things. So if you kind of understand some of the reasonings and terminology and definitions behind these, it really, really helps. So. And just like anything, there's and I didn't include it because that was in your previous lab. There's a whole book like this big on alternative terminology for neuroscience and nervous system. So there's 6 different terms for almost every structure and everything, and they have all the alternative terms. So sometimes when you're reading, you might hear a term that means the same as something else, but it's a totally different term that they use. So I'll try to point out the common ones that are the most common terms that might be to describe the same thing. So, okay, let's see if this thing, it's on. Why isn't it not? Let's see if there we go. All right. And then that's my wife, Julie. I met her at Loma Linda. I remember that first time I tried to ask her out. She was actually, I met her over a dead body, literally. I was an anatomy TA. So I went out the first day that when they had the bodies, they brought the bodies in for the new cadaver, she was a year behind me. She was occupational therapy. And I was a teacher's assistant coming in. I already had my anatomy. And so And I went in, and they had put all the names around the cadavers of who was going to be at these cadavers. So, of course, I went in and like scoped out, and I found the cadaver that had all female names around it. And I just said, this is, because they said, go choose your cadaver, what you want to be, you know, and you stayed at the same cadaver, you know, helping with that group the whole time. So this is my cadaver, this is my group. And so, but the only thing of course, she's wearing this, you know, just big lab coat thing, you know. And so the only thing I like see was her really nice tan calves. I just remember she had these really tan calves. So, hey, you know, so that's what. But then her personality made it, you know, that much better, you know. So, but I will tell you, so I graded her first exam, and she bombed. I was like, said I go, I better not get attached, you know, because so. But when we were covering the brachial plexus, you know, I go, you want some help? You know, you need some help? I think you need some help. So let's draw it out and all that. So I said, and just in case, here's my phone number in case you have any questions, you know, about this brachial plexus here. So she still has that brachial plexus with my phone number on there. So anyway, I think this is one trip we got to go on that my kids weren't, to Hawaii. And then that one, we were at Bandelier State Park out in New Mexico, where they have all these ruins and stuff. I couldn't believe they let you crawl up those ladders with no safety protection. I was like, this is kind of fun, you know, risking our lives to crawl up this ladder to these different little cliff dwellings and things like that. So she's a good sport. Occupational therapist, she works in long-term care settings. So I'm always asking her for advice, or what's going on in the reimbursement? What's the thing happening out there in the real world? So, and if I have like upper extremity OT stuff questions, she's good at telling me what to do with that. So, all right. So let's talk about the language of neuroscience. So let's talk about terms that describe locations in the nervous system. And these are terms you've mostly heard before, and some are synonymous with what you know about parts and locations within the body that you've learned about. So superior, one part is above another, situated above another part, okay? But we're talking specifically nervous system here, okay? So you'll see some changes as we get down here. Inferior is if the part is below another part. Rostral means it's towards the head or beak. Rostral means beak, so the nose, the beak, towards the head or towards the nose, as it relates to the neuraxis, okay? And we'll get to what that means. The neuraxis is, it curves and turns a little bit in the human body. It's not in line with our the longitudinal axis through our body. So we have a longitudinal axis that goes right through our body all the way straight up. Then we have a neuraxis that follows our nervous system that curves as it gets up. So that's where it gets a little, not confusing, but just a little different. You just got to know where you're at, and then the terminology kind of makes sense. Caudal is towards the tail, or coccyx in relationship to the neuraxis. Anterior is towards the front, okay, and we're talking about it related to the long axis of the body, okay. Posterior is towards the back as related to the long axis of the body. The term dorsal is towards the back related to the neuraxis, okay. So we tend to use things like rostral, caudal, ventral, dorsal more as related to the nervous system and neuraxis, okay? You more commonly hear those terms when people are talking about where one structure is in the nervous system related to another. Is it caudal, is it rostral, is it dorsal, is it ventral? So in your readings, you might hear those terms. When you're talking about parts of the body and bones and muscles and anterior and posterior, lateral, you tend to use those more with that, but they can be used interchangeably. So I just don't want this to confuse you too much. If something is ipsilateral, if we talk about an ipsilateral structure, okay, a tract or a pathway in the nervous system, means it starts on one side and ends on the same side. Some tracts, though, will cross briefly and then come back. As long as it starts on the same side and ends on the same side, a pathway or a tract, it's called an ipsilateral pathway. If it starts on one side and ends on the other side, then it's a contralateral pathway, okay? So here's a picture that helps make a little more sense of this. So if you look at the alligator on top, reptiles are four-legged animals, or quadrupeds, that their long axis through their body and also the axis through their nerve axis through their brainstem, spinal cord are all in the same line, right? And that's how that terminology was kind of originally made up, based on a organism or an animal that has a body axis, longitudinal axis, and a nerve axis that are all on the same plane, okay? However, you look at us, you know, we have a longitudinal axis that runs straight up through our body like this, but then our nerve axis actually does a 90-degree turn here, almost a 90-degree turn, if you're talking about just the central nervous system. We're really talking about brain, brainstem, spinal cord here, because we have this thing called the cervical flexure, and this happens during development where kind of our brain kind of gets a kink in it and kind of does this and comes over the top, so we're looking forward like this and sits this way. So originally it starts like this, but then it kind of gets this little cervical flexure, we call it. So the nervous system axis kind of does a little bit of a turn there, okay? From the front, the sagittal view, everything's pretty much the same, okay? So let's just go to the next picture, which I think helps you understand it. We can just focus in just this area here. So the longitudinal axis of the body, you know, goes straight up like this, okay? But then here's the nerve axis that actually has that little angle, okay, to it. And so as long as you know where you're at in the body. So if you're in the spinal cord or the brainstem, the terminology in the spinal cord and the brainstem is the same as you would use for the longitudinal axis through the body. So if you say like the anterior horns of the spinal cord, which is a gray matter in the spinal cord, they're anterior, just like our body. They're anterior to our body. There's same axis there. The posterior horns are posterior, okay? The cervical vertebrae or cervical segments are superior to the thoracic segments, okay? Or the thoracic segments are inferior to the cervical segments, okay? So that all just kind of lines up. Or something's medial or lateral. That's all through the spinal cord and brainstem, okay? So if we say the pons is superior to the medulla, pons sits above the medulla, but you could also say it's rostral, okay? So you could say the pons is rostral, it's more towards the beak, okay? And then you could say that the medulla is inferior or caudal, okay? Does that make sense? So those terms are interchangeable when you just knowing where you're at before that turns here. So if you're in the brainstem and spinal cord, the body axis terminology and the nerve axis terminology pretty well line up with each other, okay? It's just when you get into the cerebrum that it starts to get a little different, okay? So because you have this turn here, so if, if we extend this line up, let's just kind of have that reference of the body axis. But so in the cerebrum, dorsal and superior are synonymous. Does that make sense? Because this has changed this axis here. So dorsal and superior are synonymous. So if you say the corpus callosum, that connecting structure, you could either say it's superior to the diencephalon, or you can say it's dorsal to the diencephalon. It's above it, okay? But let's go back to our brainstem example. In the brainstem here, since this brainstem and spinal cord is aligned with this body axis here before this turns, if you say that the pons, you're going to say it's either superior or rostral, because rostral is also, you can say rostral up here if you're in line with the body axis. And so in the brainstem, the rostral and superior are synonymous in the spinal cord and brainstem. But when you get in the cerebrum, dorsal and superior are synonymous. Does that make sense? And then in the cerebrum, ventral and inferior are synonymous, where down in the brainstem and spinal cord, it would be inferior and caudal are synonymous. Okay. And then here, rostral and anterior are synonymous, caudal and posterior synonymous. That's in the cerebrum. So it's not, I'm probably making it more big deal of it and more complicated it needs to be, but you just got to say, I'll try not to trick you. You know, I'm not trying to like, I'm going to try to come up with a terminology that'll most confuse you about where one structure is located for another. Just when you're reading, if you're trying to read other books and other things, if somebody's saying, that's where it's hard, when they're trying to describe and you don't have a picture of where something is in relationship to another, rostral, caudal, ventral, dorsal, anterior, posterior, you just got to say, okay, where are we at? If we're in the cerebrum, if they say rostral, oh, could be more anterior. Oh, if I'm in the brainstem and they're saying something's more rostral, just means above, okay? So, and if you need to sit down with me and go through this on our own, just let me know. And I have office hours that I post in here, but I put like 1 to 3, but I'm around all the time. I never leave this place. So I have a kind of an open door policy. If you see my door open, that means you can tell Vicki, whatever, hey, can I go back see Dr. Jackson? And I'm happy to sit down with you and just take care of things as we go, okay? Any questions on that? Sort of makes sense? Medial lateral is easy. That's pretty much the same all the way through, like medial and lateral, okay? Just that rostral, caudal, anterior, posterior thing. Neuroanatomical planes, so let's talk about those. You guys already learned the different planes of the body. We have a coronal plane, which is a frontal plane, as if taking a slice through the front in this way, so the frontal plane, okay? We have a sagittal, straight down the middle, then horizontal plane, same planes that we have through the body itself. But we're primarily focusing here on nervous system, and mainly the brain, okay, brain stem, when we look at different sections. So coronal, that's this one like this, straight down, through here, okay? Then we have a sagittal, right through the center this way, sagittal, okay, a plane, and then a horizontal this way. These are all, that's a mid-coronal, a mid-horizontal, and a mid-sagittal cut, okay? Everything off of those are called parasagittal cuts, okay? So when you start making slices away from the center, they're just called parasagittal cuts, and sometimes they'll describe kind of the general location or where that parasagittal cut is. If you look at your this little neuroanatomy lab manual, there's some this is just some nice photographs to look at, but what they'll do typically, let's see if they show it, when we get to slices, the different cuts through the brain. Oh, here we go. Like this picture here, I don't have page numbers on here, but they're showing you, so the picture is actually this slice right here, this little cut through here, one of the cuts, but then they show you where they have a black line there showing you where that cut was made through, okay, and you're looking at that part of the brain through that's a coronal or frontal plane parasagittal, not paramedian, but yeah, there's parasagittal off the side here. This would be not really a parasagittal, just, it's just a paracoronal cut, paracorona, parasagittal, parahorizontal, But, and like this one here is more of an angled cut they show you, so it's important to kind of like, oh, let me look at that, how they cut that brain before I actually look at the specimen itself and see where they made that cut. Whose is that? Here's so here's our horizontal section right there. That's pretty much a mid-horizontal section through the cerebrum, okay? Got some ventricles in here. We got some basal ganglia structures actually in here that are kind of divided into there. This is a mid-coronal section, so mid-frontal section here. We have our basal ganglia. We have our thalamus actually in here, some basal ganglia structures out in here. You can't see them very well in these cuts. I'm just kind of sharing some things. And I'll be saying things a lot over and over again. Some stuff I don't expect you to know at this point, and I don't expect you to write down. I just try to give you repetition on terminology and hear it, so don't freak out if like I'll try to make sure I'm kind of like, hey, that stuff you don't have to know right now. I'm just kind of getting the repetition going. This is our mid-sagittal section here. So mid-sagittal, This is a horizontal cut through the medulla. Okay, so that's a horizontal cut through the brainstem. So we can do the same kind of cuts. The only cuts we're going to see through the brainstem are going to be horizontal cuts through the brainstem. We're not going to see any coronal cuts and those kind of things. We might see, maybe we'll see some mid-sagittal cuts. I take that back. But when we're trying to identify like little nuclei and pathways and so forth, they're all going to be these horizontal cuts through the brainstem. They look like those ink blots. Like you're just like, what? Believe it or not, you'll get to know what's in there. All right, so we're still on terminology of the nervous system. And the next thing we're going to talk about is these terms that basically, if you hear these terms, they're talking about a pathway or group of nerve fibers, like group of axons that are running somewhere or between something or going somewhere. So anytime you see this tacked on to the end of a name, like we'll talk about a thing called the medial lemniscus. You're like, oh God, freak out, but you go, it's a lemniscus. That means it's some kind of pathway or group of axons running somewhere. You may not know where that is yet, but we'll talk about that. So capsule, okay? Capsule is actually a group of neurons, okay? A group of axons, I should say. Not the neurons, not the cell bodies themselves, but there's a major thing we call the internal capsule. And we start looking at the cerebrum, and we look through a nice, what we call mid-coronal cut. There's a structure of white matter. This area right here, there's axons running through it. That's called the internal capsule. Okay, that's what so if you're capsule, they're just talking about groups of neurons, and that happens to be there's other capsular structures too that we may not even get into. And radiation is just a group of neurons or axons running from one area to another. The main one we'll talk about is the optic radiations, which are taking information from your lateral geniculate nucleus in your thalamus back to the occipital lobe, called the optic radiations. It's a white matter, these white matter pathways that are the axons that have that white coloring because of the myelin on them. A lemniscus is also just a ribbon-like. Ribbons are kind of flat, right? And so when we look at the medial lemniscus, you'll actually see it kind of has a little bit of a flattened ribbon-like appearance as it kind of like twists down through the cerebrum, brainstem, into the spinal cord is the medial lemniscal system. Okay, actually it's carrying sensory information. Proprioceptive information comes up the medial lemniscus from the body. A tract, spinal thalamic tract. That's a pain pathway. Spinal thalamic tract. That's just the axons that are running through this tract, running up through the spinal cord and brainstem. Okay. If you hear the term fasciculus, a fasciculus, we'll talk about the medial longitudinal fasciculus, okay, is a group of pathways or axons that are carrying information. And that fasciculus is a little bundle or packet, okay, a little bundle or packet of axons. A funiculus is a larger than a fasciculus. It's a larger bundle or packet of neurons. So sometimes we have fasciculi that are subcomponents of a funiculi or funiculus, okay? And so like when we talk about the spinal cord itself, there's certain groups of pathways, like a bigger part of the spinal cord is called like the funiculus, the lateral funiculus, which is a bigger region. Then there might be some fasciculi running within inside these funiculi or funiculus. So nerve. A nerve is typically has a bunch of axons running in it. So our peripheral nerves typically have motor axons, sensory axons, and some autonomic axons or fibers, most nerves, okay, until they get to the very last branches, to whether they're coming from a sensory structure into that nerve or going to a motor structure. But most nerves are a group of axons that carry both motor, sensory, and autonomic function in them, okay? And then commissures. Commissures are where two places join. These are axons that connect two corresponding areas of a left and right side typically. So commissural fibers, the corpus callosum, that one we talked about, that's the biggest commissural fiber. It's connecting the same areas on each side of the left and right sides of your brain of kind of your frontal lobes and parietal lobes mainly, okay, frontal lobes and parietal lobes. That's a commissural fiber. There's also a thing called an anterior commissure and a posterior commissure that also connect, like the anterior commissure connects more of the temporal lobes, between the two temporal lobes on each side of the brain. The posterior commissure does some more with occipital lobes and so forth. So it just allows the two halves of your brain to talk to each other and coordinate activity between each other. So those are groups of axons or pathways, okay? Then we have names for groups of cell bodies. So these are the actual cell bodies, right? You have the cell body of the neuron, which has an axon coming off of it or going to it, okay? So that when you have a big group of cell bodies all together, okay, these are typically called a ganglia, okay? Typically, a ganglia is used to refer to a group of cell bodies in the peripheral nervous system. So we're going to talk about the sympathetic chain ganglia or the dorsal root ganglia. These are little groups of cell bodies out in the peripheral nervous system. There's an exception to that, which we've already mentioned, is the basal ganglia inside of the cerebrum. But there's an effort to move those, to change that name to basal nuclei. That's why you'll hear a lot of times newer textbooks and people will call them the basal nuclei, because a nuclei or nucleus is what you typically call a group of cell bodies within the central nervous system, okay? You tend to use the word ganglia when you're talking about group of cell bodies out somewhere in the peripheral nervous system, okay? So a nucleus down here or a nuclei is referring to a group of cell bodies, not the nucleus inside the neuron itself, but the group of cell bodies in the central nervous system that has some kind of function, okay, that group together for some kind of functional reason. We also have things like laminas, okay? A lamina, you guys know what laminate is? Like when you have lamina, those are layers, or like a laminated, when you laminate something, you put something like together and squeeze something between it or layer it, or like a laminate flooring is like these little layers all stacked on top of each other. We have lamina like in our spinal cord, that the gray matter in our spinal cord, the gray matter that's kind of the inside part of our spinal cord is all cell bodies. It's actually divided into these layers called lamina, okay? They're called Rexid's lamina. And so they're just different regions. So that's just cell bodies that are called lamina in the spinal cord. And also a body. You know, if you hear the term body attached to something, okay, that's also typically a group of cell bodies, group of cells in the central nervous system, okay, a body. Any questions on that? Got it? All right. So when we're talking about describing the nervous system, especially the anatomy and surface anatomy of it, we talk about furrows and depressions. You know, just like you have a fossa, you know, olecranon fossa and that kind of stuff in your bones and different things, we have similar terminology to try to help describe the surface and parts of the anatomy of the nervous system, okay? So a sulci is a rut or a furrow. So those indentations, all those little wrinkles on the brain, the indentation part of it, those little, you know, those little spots that are kind of going inside are called sulci, okay? And that makes sense. That means a rut or a furrow. It's like a rut or a furrow, okay? A fissure, we have this thing called the lateral sylvian fissure, okay, on the side of our brain here, which is like a little bigger and deeper than your typical sulci, so it's called the lateral fissure. So it's larger and deeper than a sulci. It's a fissure, you know. Fossas, okay? We have fossas. We have a fossa in the back of our, called the rhomboid fossa in the back of our brain stem, where our cerebellum sits. There's a little indentation. When you pull the cerebellum off the back of the brain stem, there's a little structure that's kind of rhomboid in shape. It's a depression in the brain stem called the rhomboid fossa. You know, so you'll see that terminology used for to describe depressions, bigger depressions in the nervous system than a sulci or a rut. They're kind of bigger, but not as deep. Bumps and ridges, okay, so bumps and ridges, things that are, you know, bulging out or bumping out on the nervous system, okay. Peduncles, it's a stem-like connecting part. So if you hear the term peduncles, there's these things called cerebral peduncles. They're the things that connect your midbrain to your cerebrum, cerebral peduncles. They're the connecting stock between your cerebrum and your midbrain, and they're the front part of your midbrain called the cerebral peduncles. Gyrus, if you hear the word gyrus, so we'll talk about the gyri. You know, you have the ruts and the furrows, but the little rounded, bulbous, kind of curly-Q things on your brain, you know, that is gyri, okay? If you hear the term brachium, that means arm, but that's a connecting area also, a brachium or the arm. So we have a thing called like, when we get to the back of the brainstem, we'll also talk about this thing called the brachium of the inferior colliculus. And it's a ridge that goes from one structure to another between two bumps on the back of your brainstem there. And actually, if you cut into like a peduncle, or a peduncle or a brachium or something like that, or you're typically going to find axons below that, or pathways, or things, you know, the connecting things. Axons. Okay. Tubercles is more of just a bump, a little nodule, tend to be kind of smaller in nature. So we'll talk about when we get to some bumps again on the back of the brainstem. We have a lot of bumps back there, or we can imagine a few bumps. They're sometimes hard to see, but they're called tubercles typically. And if you were to go right below a tubercle, typically there's a little nuclei. There's usually a group of cell bodies below those little tubercles. Okay, and we'll get into that when we get into some of the pathways for, especially sensory pathways that run up through the back part of the brainstem. These here, we're all talking about typically surface features. Same thing here, we're talking about surface features of the nervous system. Okay. Layers we talk about typically more deeper structures. Okay. Except for the cortex. But you know, if you hear of laminas, we already talked about laminas or layers. Okay. And lamina literally means thin sheet or veneer. Okay, we talked about the rexid laminas in the spinal cord, these layers of cell bodies. Cortex. The cortex is the bark. Cortex is bark. So like the cortex of our cerebrum, it's a microscopic layer still, but it actually has 6 subcomponents or 6 little layers to it. But the cortex is that gray matter. It doesn't look gray, but you know, compared to the white matter, it looks a little darker. The gray matter, that little couple millimeter thick layer on our surface of our cerebrum, that's divided into 6 sublayers. Okay. Tectum or roof. We'll talk about what a tectum is. There's a certain cut within the brainstem where we refer to a part of the back part of the brainstem as the tectum, or it looks like it's like the roof over the top of the brainstem on the back side of the brainstem, called the tectum. And then tegmentum is called covering. And we'll talk about the tegmentum of the midbrain. The tegmentum is of the brainstem, I should say, not just the midbrain, but that's kind of like the meaty inner layer, the tegmentum. Even though it means covering, we'll show you that division when we get to those structures. But those just mean layers. That's what I want you to take away from that, layering through the nervous system. Doing all right? Staying up with you so far? Good. Okay. We're going to go through this stuff fairly quickly and see if we can get into just doing some surface anatomy here today. Cerebrum, big picture. We're going to do a whole 2 lectures on the cerebrum at the end and get into all the detail, but this is just big picture. Cerebrum, this guy right up here, okay? Not the brain, just the cerebrum, not the brain. Member includes the cerebrum plus the brain stem plus the cerebellum and all that stuff. We're just talking cerebrum, which includes those basal ganglia and basal nuclei deep inside. It also includes, so that's what it includes. What does it do? Cerebral hemispheres process, lots of processing. Processes sensory, motor, memory, reasoning, language, intelligence, personality, emotions. So that's what's kept going on up there. Lots and lots of processing. Okay? You have those 4 primary lobes. Hopefully you've heard this before. The 4 primary lobes of the cerebrum: the frontal lobe, the parietal lobe, occipital lobe, and temporal lobes. Okay? Occasionally you'll hear some text refer to what's called a limbic or insular lobe, a 5th lobe. And we'll show you that tomorrow. You can take your brain, and on the side of the brain there's this thing called a lateral sylvian fissure. If you open that up, you'll see some gyri down deep in there, and some people refer to that as the insular lobe or the limbic lobe down deep inside there. So I just point that out because you might read that. But most people talk about 4 main lobes. The lateral sylvian feature is the big, deep fissure on the side of the brain between the parietal and the temporal lobes. We'll show that in a minute here. We have a longitudinal, cerebral longitudinal fissure that is really deep and divides the two cerebral hemispheres. That's a big feature that you need to know about. So the cerebral longitudinal fissure. Corpus callosum, we've talked about it already a few times. It's that connecting structure that is connecting a lot of the brain from left to right. We have the surface, which is composed of gray matter, the cortex, cell bodies, right? The gray matter, cortex. And it has 6 sublayers, which we won't get till we get to the cerebrum at the end of the course. Deep to the cerebrum, most of what is deep to the cerebrum is white matter, okay? That's all the axons that are running to and from the cortex, right? You have sensory information going up to the cortex, you have motor and other information exiting or going away from the cortex, so you have afferent axons and neurons bringing information towards the cortex, acquiring afferent, and you have efferent axons going the other way from the cortex to go supply whatever other function in your body. That's the white matter, okay? We talked about that internal capsule. There's a big group of axons that come down and kind of get squeezed down in the cortex. That's called the internal capsule, which is just a lot of those white matter fibers running to and from the cortex, okay? Then we have our basal ganglia, or now termed the cerebral nuclei or basal nuclei. So this is where you get into all this. Some people call them the basal nuclei, some people call them the cerebral nuclei, some people call them the basal ganglia. All synonymous, okay? The basal ganglia, it's a plural, is composed of certain subcomponents, and you don't have to know this right yet, but the caudate, globus pallidus, and the putamen are the main subcomponents of the basal ganglia, or the basal nuclei. The diencephalon, even though it's considered a separate part of the central nervous system, one of the 7 main parts, it's still actually a subcomponent of the cerebrum. Functionally it's part of the cerebrum, okay? So the diencephalon, two, thalamus and hypothalamus primarily. So it's primarily these 2 guys, but it really also does include, some books and some things refer to also the epithalamus and the subthalamus as also being parts of this thing called the diencephalon. However, most people consider just these 2 major components, the thalamus and the hypothalamus, because it's 2, but you'll hear the epithalamus and the subthalamus are also right there and functionally related and have connections with the diencephalon, so some people group all these together as the diencephalon. I'll try not to ask questions on the exam that would confuse you on that or try to trip you up on that. It's not that important to us as a physical therapist, but just from your own reading and knowledge standpoint. So the diencephalon does a lot, okay? It's a major relay center for sensory, motor, okay? It's like the secretary of your brain. It does a lot of like filtering and processing. So like all the sensor information coming up to your brain and even some of the motor circuitry, loops, there's some loops in our brain, you have to go through the thalamus first. You get filtered by the thalamus first, and the thalamus sometimes can decide whether you make it up to the brain for conscious awareness or you don't. So it's just a kind of a relay structure, okay? It's a central receiving relay structure in the brain, okay? The hypothalamus, it has a big role in autonomic nervous system function, okay? And all these things related to homeostasis, reproduction, eating, and growth. The hypothalamus and its connections with the pituitary gland are the master controllers of all the hormonal and a lot of autonomic function, okay? And that's the hypothalamus. So the thalamus itself, the thalamus proper, is that egg-shaped structure that's primarily for relaying motor and sensory, okay? So thalamus, relay structure, motor, sensory. Hypothalamus here, it's got to do with all this stuff. Homeostasis, reproduction, eating, and growth. Hypothalamus is heavily involved with that. The epithalamus, also known as the pineal gland. So the pineal gland and the epithalamus are the same thing. So again, that's that alternative terminology that you can talk about, the epithalamus and pineal gland. Pineal gland plays a role in regulating the pituitary and the adrenals. Okay, so it's primarily influencing hormonal control and production. The subthalamus, right here, is another thalamic component. It's got that suffix of thalamus on it. It's an alamus type of structure. It's primarily involved in movement or motor control because it is more, this guy is actually more associated with the basal ganglia than the rest of these three other components. So the subthalamus doesn't really do much to work with those other three components. These other thalamus, hypothalamus, and epithalamus are more cohesive in what they do. The subthalamus is kind of out there on its own, hanging out with the basal ganglia, and has some control there, and circuitry of mainly over motor control. Okay. Just start giving you some three-dimensional perspective here where all this stuff is. This is cerebrum we're talking about, right? So here's the cerebrum, all the gray stuff there. Deep within the cerebrum, we have the basal ganglia, which is the yellow stuff. The yellow stuff, and we have basal ganglia on the left and on the right. So you see, this is the left basal ganglia, then the next one right next to it. They're right next to each other. There's a little tiny space between these two things. There's a little sliver of space, but on each side, you have basal ganglia on each side, deep in there. And then you also have a thalamus, actually. So you have the two thalami sitting right in here, right next to each other. And there's a little tiny space called the third ventricle between the two thalami. So the two thalami, the diencephalon, are sitting right here, hypothalamus and thalamus. And then the basal ganglia are kind of sitting just a little bit more laterally and kind of enveloping and curling around and over kind of the top of the two thalami. Okay, so the most medial are the two thalami, the diencephalon, then a little bit more lateral, and sitting just up a little more lateral and a little more anterior are the basal ganglia, kind of wrapping around the thalami. Okay, these are different parts. Like this part here, this is the basal ganglia. Looking at the very outside of it, that's called the putamen. This whole structure here, this kind of a circular C-shaped structure, that's the caudate. Deep to this putamen, you can't see it, but I'm just going to kind of make a little dot. Deep to this is a subcomponent called the globus pallidus. It's a little bit deep to that. You can't see it there because it's being hidden right now. Then you finally get to the thalamus, sitting even a little more medial than that. Okay, and we'll see this in cross sections how this all lines up. So that's just for the left side. Then you have the same thing on the right. Okay, and that was really hard for me to wrap my head around. These main structures, how are they sitting in there three-dimensionally and that kind of stuff. This is that mid-sagittal section. Here's our thalamus proper. Here's our hypothalamus. The pineal gland sits right out here, the epithalamus or pineal gland, but it's not on there. Here's our pituitary gland sitting down here that's connected to the hypothalamus. Okay? You can't see the basal ganglia here. The basal ganglia are sitting deep inside here, right? We're actually cutting right through the middle of the cerebral longitudinal fissure. We've split this, so all we're looking at is that we're looking at the medial surface of the diencephalon. And we see the corpus callosum here, but the basal ganglia structure is just a little more deep. You'd have to actually do a parasagittal section. You'd have to cut a little farther over before you hit that basal ganglia. Okay, does that make sense? Still on the cerebral hemispheres, just let's talk about lobes, just review basic lobes. It's kind of nice just to have this basic understanding, is that here's our frontal lobe. All this blue area is frontal lobe. Motor and personality. If you just know those things and we start talking about what's going on where, if you know that, that helps you just understand basic what happens in the frontal lobe. That's where you drive mostly voluntary motor, so where you're actually making the choice to move or do something voluntarily, and also personality and freedom of choice and executive functioning and those kind of things. I want to do that because, and I'm going to do this. And then also personality are associated with that frontal lobe, okay? Temporal lobe, right down here, the orange or lighter orange here. Memory, okay? Deep inside the temporal lobe is a structure called the hippocampus, which is very important for memory, especially the type of memory you're doing right now is declarative memory, the type of memory of memorizing facts and remembering those kind of things. It's not so important for motor memory. That's a different type of memory. This is for declarative type memory. And then auditory. A lot of your information processing when you hear something and you're making sense from an auditory standpoint, hearing is mostly located right around that area in the temporal lobe. Okay? Parietal lobe, the green area right here. Sensory, it's a big sensory area and integrates a lot of information. Sensory, somatosensory from the body. Soma is body, somato is like from the body, so proprioception, skin, that kind of stuff. Somatosensation, but also it shares borders with, the parietal lobe shares borders with the frontal lobe, temporal lobe, and the occipital lobe. So it's very integrative in function. It can integrate information and make sense of things. So when you read something or you hear something, it's not this part of your brain, the occipital lobe or the temporal lobe, that actually makes sense and gives it meaning. That information is transferred up to the parietal lobe. It puts it all together. It says, oh, that's a word, and I understand that word to mean this, or that's something I read, and that's actually not just black lines on a paper. It's a word, it's a language, and your parietal lobe makes sense of that and creates a language that you understand, and those kind of things. So the occipital lobe and the temporal lobe take that auditory or visual information and just say how light, how dark, contrast, sound, the amplitude of the sound, the pitch, all that kind of stuff. But the parietal lobe, oh, that's somebody talking to me, then it means this. That's what it does more of, okay? The occipital lobe is big, and it's primarily vision. And we are very heavily visual creatures, We will default to vision to a fault sometimes, a lot of us are very overly dependent on vision. As you'll know, like when you're sitting at a stop sign or a stoplight, and even though your body is not sensing any movement, if the car next to you starts to creep up, you might think you're going backwards and you're just slamming on the brake, even though other sensors of your body are not telling you that you're rolling backwards. If your vision says you're going backwards, you're going to default a lot of times to vision. And that can mess your patients up. Sometimes patients will get in a sensory environment. Let's say they can't feel their feet, so they're really relying on their vision, but then they get outside, it's dark, or they get up at night to go to the bathroom, they don't have that visual, and they're over-relying on their vision, but when they don't have it, they're going to fall. So we got to make sure that they're not over-relying on vision. And then that insular, remember that insular lobe, that fifth one that some people talk about, this autonomic, visceral, it's got autonomic and visceral functions. So there's that, there's that lateral sylvian fissure on this brain. This is the lateral sylvian fissure right here. But if you take your fingers or some forceps and you open it up, you'll see some more gyri and sulci in there. That's the insular lobe. Okay, so that's a fun fact you can show all your friends. Yeah.
As far as structures and I guess the number of certain structures, why are some people more capable or I guess smarter than others? Like, do all people have the capability to, for example, learn what we're learning?
Within reason. I mean, some people, we all have the structure itself, you look at the gyri and sulci, and you look at things, you probably couldn't tell there's a difference between somebody who's really good at neuroscience and somebody who's not so good at neuroscience. They would look very similar. But at the connections themselves, some people, and that's, some people are better at learning declarative types of information. Some people are better at motor learning and more coordinated. But all of us have the ability, even if we're weak at something, to maximize or enhance our ability, even though we don't have the natural ability or born with that ability. And it's a matter of trying to find what works for you. But some people will never be good like test takers, or certain types of test takers, whether it be like, spitting back facts on a multiple choice test. They might be better on a conversational type style of demonstrating learning. So all of us have our strengths and weaknesses, and that kind of what makes the world go around, and makes us all the diverse creatures we are. Is this, why it's we have so much more to learn about this. But see, that's the stuff I wish I knew the answers to. All right, let's do this. How we doing here? I'm just trying to see where we're at here. Let me go. What happened? Let me go back here. There we go. Let's do some lateral surface features, and then we'll take a break. Okay, and we'll come back and hit some medial surface features and so forth. Let's get through these. These won't take us very long. Pretty easy. And this is so tomorrow we're going to have specimens in here. I'm going to bring about 7 or 8 hemispheres. You're going to divide up into groups of 4 to 5 people. And we'll just kind of get around. I'll just bring them in here on trays. So wear what you want to tomorrow. It shouldn't get, unless you get crazy, you shouldn't be splashing too much. And I'll have them all ready to go, already in a tray. I'll try to wipe things off. We'll just bring them in. I'll have them positioned over here. You just come send a representative to come grab your specimen. You have a pointer. If you want to touch, I can have some gloves, or if you got some gloves, bring them. I appreciate that. But I'll try to have a few extra gloves up here so you can touch. Somebody's going to need to manipulate it and flip it around, but then we'll have some pointers so you can just kind of point to structures and so forth as you're going through that. And we're going to do all this again tomorrow. We're actually going to do it right now, but we're going to have these same slides up, and I'm going to walk you through it all again tomorrow, okay? So, and your quiz tomorrow will be either this view, a lateral view of the hemisphere, or this view, the medial view of the hemisphere, but it'll be a line drawing. And it'll be identify structures. What I'll have is actually pointers, lines that have numbers associated with them, and then below the picture we'll have the actual names of the structures, and you just match the numbers with the names. That's your quiz for tomorrow. It's either this view or this view. And that's what your quiz is for tomorrow. All right, cerebral longitudinal fissure. We can't see it on this. The cerebral longitudinal fissure is that big, deep one here that when you cut through, that mid-sagittal cut is what you're cutting through. Lateral sylvian fissure. I'm going to change this color to yellow, make it a little easier to see. Lateral sylvian fissure. Right there. Central sulcus. Central sulcus. Every brain is a little different. Should generally be in the right area, but every brain just is a little different. This is actually not the best brain to show some of this, although maybe it's good because it shows that they're not always clear cut. The line drawings you get will be nice and fairly clear cut, almost like crayon color kind of things, at least for tomorrow. Central sulcus is this one here. When you get your brain tomorrow to look at, as you follow up what you think is a central sulcus, what generally the central sulcus does, if you know it's a central sulcus, it'll actually go up across the top of the brain and just go a little bit to the medial surface of the brain, and then it'll dive posterior a little bit. That it'll be a little slit going posterior like that, and that's generally how you know you're in the central sulcus. It'll go all the way over the ridge or the crest on the medial, and it'll end there, but it'll dive backwards a little bit. Okay. That's the central sulcus. Precentral sulcus. You jump one sulcus befront of the central sulcus. So the first two structures you find are always your lateral sylvian fissure and your central sulcus. Then if you jump one sulcus forward, you get the precentral sulcus. Sometimes it's not always a clean cut. I would say that probably both of these structures are sort of his pre or her, it's precentral sulcus, okay? But we're just going to kind of draw a line in there. That's the precentral sulcus. And if I do show you a picture for the lab practical, it'll be pretty clear cut what I'm trying to show you or represent, okay? But it's not always a perfectly aligned. And sometimes you have to jump over a gyrus, which we'll do here in a second here, for the post-central sulcus. So we'll come back one from the central sulcus and find the next area where it looks like we can kind of follow, and then we have to kind of jump over this gyrus right here. So this would be the post-central sulcus. That's actually making what's called a post-central gyrus pretty big, bigger than some brains are, okay? Some brains don't divide it into that big of a section, okay? Preoccipital notch. There's a little notch right here. It's just kind of almost some brains you have to imagine it or know. So here's your cerebellum sitting right here. So it's about, 2/3 of the way back above the cerebellum is this thing called the preoccipital notch. And that's one of the things that helps you identify where to draw your line for the occipital lobe, okay? You actually have to connect your line with another fissure or sulci on the medial surface that comes up from the other side is how you connect your dots to find your occipital lobe, okay? So that's a preoccipital notch. It doesn't have really any good functional significance other than it just helps define where that occipital lobe is, okay? Now, when we define these sulci here, it also helps us then define these regions of the brain or gyri, okay? So the first one makes sense, is the precentral gyrus. It's the gyrus just in front of the central sulcus, precentral. It's precentral gyrus. And then also we have back here, what do you think this is called? Postcentral gyrus, okay? So those a lot of times these make sense, which is helpful when they do. Not all the time, but they make sense. So from a standpoint of function, these are critical right here. Precentral gyrus is primary motor, okay? This is where the cell bodies start that have an axon that goes all the way down to your spinal cord to then connect in your spinal cord to the anterior horn cell that then will go out to make your muscle move. When it's mainly a voluntary conscious motor act. So this is mainly this part of your brain, this primary motor strip is primarily voluntary motor. You choosing frontal lobe, I want to wiggle my finger, I want to do something. When you start getting more automatic movements and reflexes and adapting to postural destabilization, more of that control gets shifted to the spinal cord and brainstem level. But it's more the discrete movements. I'm purposely kicking my leg out, moving this joint individually, moving my fingers in a very specific, voluntary way that this primary motor strip is driving that, okay? And we'll talk about the homunculus, which is where different regions of that gyrus are associated with different parts of your body, okay? And then the same thing is true for the sensory strip, okay? So the sensory strip, this is conscious sensory awareness. If information makes it up to that sensory strip, you are consciously aware of it. Whether it be pain, a tickle, an itch, knowing like if I'm standing here, I can tell you like about what position my feet are in, how much weight if I focus on it, I can say I feel about this much pressure on my feet. That's information that's getting to that primary sensory strip. There's a lot of other sensory information that's going to parts of my brainstem and cerebellum that I have no conscious awareness of, but they're just as important. But that primary strip, sensory strip, is where conscious awareness arises. Okay, and you have to, before you come up to that primary sensory strip, you got to stop by the thalamus first. You don't get to that area without stopping by the thalamus when we get to those pathways. Okay. And then the other one I wanted to point out was just this area right here is the superior temporal gyrus. This is where that primary auditory area is right in here. It's on that very top edge, just next to the sylvian fissure is the primary auditory area. It's located within that superior temporal gyrus. And just for kicks, you can divide this. There's actually a sulci that runs right here, and this divides you into a superior, middle, and inferior temporal gyrus. Okay. This is called the lateral sylvian fissure. This is the superior temporal sulcus. This is the inferior temporal sulcus. So some of this stuff, even if you didn't know it, you could reason some of this stuff out for the most part. Okay. And there's actually some sulci that run right in here on the frontal lobe. You can kind of divide the frontal lobe into some similar regions, but we won't get into that. That's lateral surface. Not too bad for the lateral surface of the cerebrum. Any questions on that? Okay. It's 11:01. Come back in 10 minutes, 11:10, and we'll do the medial surface, and then we'll probably wrap it up. Let you out a few minutes early. We got to beat the rush up to the 5th floor to get food, right? Well, it's nice, warm enough. It's not too bad to walk to Brown Street today. Okay, let's look at the medial surface of the cerebrum, or brain. This is really the brain, because this has got the cerebrum, cerebellum, and the brainstem also. We're looking at so a lot more to look at here. A little more intimidating, but not too bad. So let's just kind of go through that. Let's start with some of the big, most obvious features. That one we talked about previously is this corpus callosum, outlining it here. That whole structure there is the corpus callosum. It's got a little bit of a C shape to it, corpus callosum. Kind of helps me remember C, corpus callosum. You will, on the videos, you do see my drawings on here. This is like that's videotaping the whole screen, so you'll see that if you watch the videos. It has different parts to it, okay? It has a rostrum, the beak of it, which is actually, that little tip right there is the beak or the rostrum of it. It's kind of more rostral. It's not the most rostral part of it, so that's a little confusing, but it kind of curves around, and that tip there is more the rostrum here. This part through here, this is called the genu. It's the bend. The genu is like a bend. So that's the genu is right in here. So this little area here. This chunk here through the middle here, this is all the body. And then this round part on the end is the splenium. Okay, so it has 4 subparts to it. Functionally, those subparts don't mean a lot to us. That's just, you should know and be able to identify the subparts of that. But those different regions tend to be associated, like, this splenium tends to be more in this back part of the parietal lobe. It's communicating between the 2 posterior portions of the parietal lobes on each side. This body here is communication between both some of the frontal lobes and some of the front part of the parietal lobe. So, but anyway, just FYI, remember I said that central sulcus comes over the top ridge and then it dives backwards a little bit? That's the central sulcus coming over the top and diving backwards a little bit here over that ridge is what we're seeing there on top. Let's talk about diencephalon. So here is the diencephalon. So this here is the thalamus. This little bump right here, on the thalamus is called the intrathalamic adhesion. So you've got a thalamus on each side, and most of us have this little connecting stalk between the 2 thalami called the intrathalamic adhesion. But there are a percentage of people that don't have it, and it doesn't mean you've got problems or you're going to have a problem. So it doesn't have a lot of functional significance to us, that little but everybody asks, what's that little bump on that? That's not the it's the intrathalamic adhesion. There happens for most people have a little adhesion or a little connecting part between but you don't have to have it and be normal. And then this whole area here is the hypothalamus below the thalamus. Okay. There's a little white matter structure here called the anterior commissure. It actually has fibers that dive down to, here's your temporal lobe down here, and then it comes over to this other temporal lobe on the other side and connects the two temporal lobes. So there's some connecting commissural fibers through that anterior commissure that are connecting the two temporal lobes through there. Okay, it kind of like they kind of go down like this, then come up like that and go down to the temporal lobes. So it's some communication between the two temporal lobes. It's through that anterior, the AWC, anterior white commissure. Whoops. So there it is right there. I'm just going to point this out while I'm in the region, because people ask about this. This little structure here, that looks like almost like a mini corpus callosum, that's called the fornix. Most of your brains will have that torn off. As there's a little membrane here, that's kind of, and you can see the cut edge of it right there. This little membrane here is called the septum pellucidum. That's also typically gone. And if I were to cut that off or flip it back, we'd be looking into a hole there called the lateral ventricle, where you have cerebrospinal fluid. So most of your brains tomorrow, this septum pellucidum won't be there, and this fornix won't be there. This is all typically torn off, and you just have a hole, open hole there, the lateral ventricles in there, okay? So we have these, and we'll get to the ventricles here later in this, or tomorrow when we talk about these, so, okay? The parietal occipital sulcus is the next structure here. So this is the parietal occipital sulcus, and it's almost like a fissure. It's really easy to find. It's really deep and obvious. So this is the parietal occipital sulcus, and that's dividing the parietal lobe from the occipital lobe very easily on this medial surface of the cerebrum. If you continue the line, if you go down the lateral surface of the cerebrum and you find that preoccipital notch, and you draw an imaginary line up to connect with the top of this parietal occipital sulcus, that's how you can kind of define the occipital lobe on the lateral surface of the cerebrum. So that's the parietal occipital sulcus. Staying in the occipital lobe, this right here is the calcarine sulcus. It's almost got a little bit of a hook-like shape, calcarine. Is the calcarine sulcus. That divides this into two major, so if we take, here's our parietal occipital sulcus and our calcarine sulcus. That divides us into our two major gyruses on the medial surface of the occipital lobe. It's really not called a gyrus, but this is just called this whole region is called the cuneus. This whole region here is the cuneus. This region right here, you can kind of, this is the lingual gyrus. Lingual means tongue, and it kind of looks like a little bit of a tongue. Doesn't that from the side? Looks like a tongue projecting out. So this is the lingual gyrus right here. The reason, just to kind of know those from a clinical standpoint, is that your primary visual cortices, when vision comes back to your cerebrum or back to the occipital lobe, the first place it makes its connections in the cerebrum is right here. It's on the lips or the edges of the lingual gyrus and the cuneus. So this is your primary visual areas, are right in here, right around the lips, so the edges of that calcarine sulcus on the cuneus and the lingual gyrus. And so when your vision comes back there and you first recognize a visual stimulus, it's at that location, okay? And when we get to vision, and Christina will talk about, everything is flipped upside down and backwards, you know, at that point. So this side of the brain is seeing the left visual areas of your, and it's also this lower part here on the lingual is seeing the superior visual field, and this upper part here seeing the inferior visual field, but your brain puts it all together, so it's normal. So, but just confusing for you as a student to learn some of those things because everything's upside down and backwards until your brain makes sense of it and makes it upright. Okay? So, the cingulate gyrus and sulcus, okay? This right here, I'm going to a little bit of a connecting here. So there's a gyrus that this is the cingulate sulcus. I'm outlining cingulate sulcus, and it actually goes all the way around like that. It's C-shaped, cingulate. It's also C-shaped. So there's a sulcus here that runs right here, kind of that middle, all the way through from frontal to occipital lobes, called the cingulate sulcus. And this guy right here is the cingulate gyrus. Cingulate gyrus. It's all wrapping around the middle of your cerebrum there on the medial surface. This area has to do with limbic system function, emotional stuff. Okay, so limbic, attaching emotion to experiences and those kind of things. And you think about, these are kind of like these they're like at the center heart of your brain, and they're kind of like wrapping, enveloping. I'm thinking like hugging, and the heart, and like feeling emotion is kind of at the center of your brain like that. So that's helps me remember this limbic system function. Okay, is this cingulate gyrus area, and even this fornix is also limbic system function. Okay. Is related to limbic system function as the fornix area. All that central stuff and that wrapping, except for the corpus callosum, is just more connections between the two sides. Then there's also, this pen is so small, I'm trying to find the buttons on it. There's a sulcus right here, right between the cingulate gyrus and the corpus callosum. That's the callosal or callosal sulcus. Okay, it's just above the corpus callosum. It's the little sulcus above the corpus callosum, so it's called the callosal sulcus. Did I even have that on there? I don't think I had that listed on there. The next thing we're going to look at here is the optic chiasm. Okay, so the optic chiasm. Here's our optic nerve. Some of your specimens tomorrow will have a little bit of a tag end of an optic nerve that's been cut that goes out to your eyeball. Some of your vision, as it comes in, crosses. Remember I said it crosses over to the other side, so your right half of your brain sees your left visual field. So there's some crossing going on there, and a chiasm is a crossing. Chiasm is crossing, so it's the optic chiasm. And so right here, this little white area here, that little round cut-through point there, that's the crossing point. Your optic nerves come in, and when you cut right down through the middle of that chiasm, where there's some of those axons that are crossing through there, that's the optic chiasm. And that is just below your hypothalamus. Okay. So it's easy in this area to get messed up, right in this area here, with some structures. So let me just kind of zoom into this area and point it out again so you don't get confused. Here is the anterior white commissure, okay? It is more anterior, and it is just this thing below the fornix or just below the lateral ventricle, okay? Optic chiasm is right here. So they're both like these white matter areas that can look very similar, but optic chiasm is below the hypothalamus, okay? And there's also, a lot of times you'll see this little tag end of a nerve coming off of it that gives you a clue that's optic nerve, okay? This structure right here, it doesn't matter to us as a physical therapist. It's called a mammillary body. So remember, bodies are just, so there are some nuclei in here. They don't know exactly what it does, but they assume it's some kind of limbic system structure. And some connections within the limbic system, again, that emotional stuff, all this stuff. And so, but that's what that is. But then here we have interthalamic adhesion. That's the adhesion right between the two thalami. So it's just easy to get these four structures confused. So just make sure you kind of clear about that. And, most of these have, the only one that really has much, functional relevance for us is this optic chiasm. The rest are kind of just, great if you have them. If you don't, probably physical therapy standpoint, not so critical. Brainstem. So let's just define our brainstem here. This whole structure, that's the midbrain right there. All of that. Okay. This whole structure here is the pons. Okay. You'll see some spaces in here. These spaces, there's a connection between these spaces. Those are part of our ventricular system. Okay. We have our lateral ventricles up in here. This ventricle right here, our lateral ventricles are ventricles 1 and 2, basically, our two lateral ventricles. There's a little ventricle, a little space between the thalami, a little sliver of a space about this wide that has cerebrospinal fluid in it called our third ventricle. And there's a thing called a cerebral aqueduct, a little hole, an aqueductal hole that connects the third ventricle with this space down here called the fourth ventricle. Okay, so cerebrospinal fluid comes out of your lateral ventricles, goes down into your third ventricle, down to the cerebral aqueduct, down to the fourth ventricle, and then it actually, most of that cerebrospinal fluid comes out and gets out to the outside of your brain just through a couple little holes or ports just below the cerebellum. Okay, and then it circulates around the outside of your brain. But you're seeing that in there. I just wanted you to, we don't have to know all that right now. I'm just kind of pointing it out so when you see it tomorrow too, you just take advantage of having that opportunity to kind of get a feel for that. But again, midbrain, pons, this front part right here, this is the front part of the pons, is called the basilar part of the pons, that bulbous basilar part of the pons, that rounded front part, okay? Then here's our medulla down here. This whole big central area, let me kind of get rid of that a little bit again here. So when we start talking about kind of layers of the brainstem, which we'll get to when we get to the brainstem more specifically, but in the sagittal view, you've got the front part of the brainstem right here, which is mainly this basilar pons. The meat or middle is the tegmentum. This whole area here is the tegmentum of the brainstem, this meaty midsection. But this tegmentum, in a sense, provides a covering over the basilar part of the pons. It's kind of like a covering because it's angled forward like this, so it's kind of like a covering. Remember we said tegmentum means covering? That's what they kind of mean there. It's like it's kind of covering over the basilar part of the pons. And then it's this whole area here. This little guy here, sticking off the back here, we'll talk about them in a second here. Those are the superior and inferior colliculi. Those are the back part of your midbrain. They're also known as the tectum of the midbrain because they're the roof. They're like a roof over everything else. They're like the tectum or the roof of the midbrain over the top. So that's the tectum of the midbrain, which is made up of some other structures. Again, don't freak out on that. Just kind of starting to introduce you to the terminology, and we'll do lots of repetition of that. Then obviously this heavily foliated structure back here is the cerebellum. Okay, and just all you need to know about that right now is that's a cerebellum. It does have this what we call an anterior lobe right here. And there's the division there, the anterior lobe. Then all this huge rest back part is the posterior lobe of the cerebellum. Cerebellum, important for us. Not that we can do a lot about it. We do a lot of our, well, I should take that back. A lot of our motor learning we do in practice and getting somebody better skilled at something, a lot of that improvement is occurring at the cerebellum unconsciously. You're just providing the right practice environment so that it happens unconsciously. But that's our coordination center, our unconscious coordination center that helps regulate coordinated movement without us thinking about it, okay? It's our error detection feedback system that is subconscious. The problem with it is if you have damage to it, it is really hard. If you lose your error detection system, you don't have a way to check yourself unconsciously, and so it's really hard to rehab somebody with a cerebellar problem. It's not impossible because you don't usually wipe out the entire cerebellum. You still have some cerebellum left that you can train and enhance, and you can use other compensatory systems. But if you lose your cerebellum, it's really hard for people to even be able to learn new movements or gain better skills if they don't have that unconscious error detection correcting system built in. And so that's all I say is cerebellar patients are challenging, but they can also be, you can really do some cool things. And now some of the new technology out there, have you seen, my wife works with this, she's an occupational therapist. So cerebellum, if somebody has a cerebellar problem, they have a lot of what we call ataxia and tremor, and I try to, and the closer I get to something, I'm trying to make error corrections, the worse and more amplified it gets. They're trying to eat and they can't bring their hand to their mouth and they're spilling their food all over the place, but they have these, silverware that you can now use that actually has a built-in, it'll compensate for every oscillation so that the fork or the spoon stays level no matter what and it's amazing. And she says they've gotten a few of those for their clients. It's just like magical for their quality of life, because if you can't feed yourself, that's really tough. It's tough on you, it's tough on your family, so being able to feed yourself effectively is huge. Medial surface okay? Kind of, sort of? You'll know it by tomorrow, right? At least the major stuff in there. The more important things are what you want to focus in on the lateral and medial surface. Real quick, lower part. Since tomorrow we'll be just looking at, you'll be looking at just like one half of a brain. Sometimes it's harder to see some of this stuff, and some things get boogered up and ripped off and those kind of things, so some of you won't have all this stuff. But one thing you might have is this little thing right here, olfactory bulb and tract. So here's the olfactory tract and the olfactory bulb. It's one of the few cranial nerves that comes right out of your brain. That thing doesn't come out of the brainstem. It comes right out of your brain, and it goes straight to your limbic system, the olfactory bulb and tract, and that is information. So there's a reason why smell is a very primitive sensory thing, and why you also associate lots of limbic and emotional types of things with smells can really drive primitive kind of memory and grandma's apple pie, that kind of stuff. And most of our taste is smell, very little of our taste. So when you have a cold and you have a blocked up nose, you don't have a lot of taste, and that's why a lot of older people, when their olfactory bulbs start going bad, or they're a heavy smoker or just older, food loses its taste. It's no fun to eat anymore, and that's why it's hard for someone even to feel like they want to eat, because you don't get really much enjoyment out of it anymore. Okay. If you take that olfactory bulb and sulcus and get it out of the way or rip it off, then below that you have a sulcus that runs in. Okay, that's the olfactory sulcus, where that's laying is in that olfactory sulcus. The olfactory sulcus, along with, here's the longitudinal fissure that goes between the two cerebral hemispheres. If you extend that up, this defines these two gyruses here that are called the straight or rectus gyrus. There's a rectus or straight, kind of like your rectus abdominis right here. They kind of run straight up and down there. It's called the rectus gyrus. It's more executive, functioning, reasoning, decision-making kind of stuff, frontal lobe stuff. Optic nerve tract and chiasm. So here is our optic nerves coming off here, the cut ends of our optic nerves that go to our eyeballs. Okay? Some of that information crosses right here in that optic chiasm. So remember when we looked at that other view, we were looking through a cut right through the optic chiasm. We were looking at the cut edge of that optic chiasm, kind of looking at that angle there and seeing that cut edge there. That's where this crossing was happening. So that's the chiasm, is this area right in here is the chiasm. Not that little guy there that's in our way. This little thing right here, this little nub end of a thing right here, that's the infundibulum. That's the little stalk that normally sits there is your pituitary gland. Pituitary gland sits right there. But when you take a brain out, the pituitary gland sits in this little saddle-like structure in your brain called the sella turcica, and it's got a little membrane over it, so you can never, it always stays in there. When you pull the brain out, you rip the pituitary gland off, and you have just a little infundibular nub left over. So some of you might have an infundibulum, although when you do the cross section, when I cut through there, drawing on the wrong screen, cut through there, sometimes I'll make the cut and you'll get the infundibulum, or sometimes you'll see you won't have the infundibulum depending on how good that cut is through the midsection. It's hard to cut right through the middle of the infundibulum. It's such a small little tiny structure. And I may take a brain out this afternoon, but I will provide an opportunity or two sometime during this semester, and I'll do it at a time when you guys are available, if anybody wants to watch a brain get taken out. Or if you want to do it, I'll show you how to do it, and then I might have you take a few out for me at the end because I'm always replacing our specimens because they get worn out. So you're welcome to, I'll try to do that so you can watch if you're not over, with anatomy already and don't want to ever go back in there again. So that's optic nerve. Oh, then after you get past the chiasm, the next part here where it goes off is called the tract. So optic nerve, chiasm, and tract. And those all referring to bundles of axons. A nerve is a bundle of axons, a chiasm is a crossing point of some axons, and a tract is axons. And then these eventually go back to the little bump off the back of the thalamus. You can't see it here. I'm just kind of, the thalamus is deep in here. There's a little bump off the back of the thalamus called the lateral geniculate nucleus. It connects there, and then these little radiations go to the occipital lobe called the optic radiations. And that's how it gets back to the occipital lobe. But we shall talk about that later. All you need to know is surface right now, just surface anatomy, okay? Parahippocampal gyrus, okay? So this structure right here, and the cerebellum and brainstem are sitting there. If we took those off, you would see this would continue all the way around. This is the parahippocampal sulcus I'm defining here, but that then helps define this gyrus. That is all this area here. If we remove the cerebellum, is called the parahippocampal gyrus. Okay? It's also associated with the limbic system, okay, and memory function. So all these structures that are kind of curve-shaped, close to the heart of the brain, seem to like to kind of be towards limbic system function. But deep inside of these, deep to these structures, inside of here, and deep in here, and actually that kind of extends out in here, is your hippocampus, which is a deep structure. Cell bodies that are important for memory, that declarative memory, is that hippocampal region or hippocampus. But that's deep. That's not a surface structure. It's deep inside of there. Inside, kind of deep to that within that parahippocampal gyrus. Oops. The uncus, right here, there's a little bump right here and right here. It's the most medial protrusion of the parahippocampal gyrus. It's that little bump there. I point this out because this uncus, you can see there's a little tag end of a nerve right here. That's the third cranial nerve. That's the oculomotor nerve right here. The oculomotor nerve goes to drive your pupils, it helps move your eyeballs, but it also dilates, constricts your pupils through the oculomotor nerve, okay? And so you ever, like somebody who has a head injury, and you go to check and see if they've got a blown or dilated pupil. What you're looking for, if they do have a blown or dilated pupil, there's actually a membrane that sits right above the cerebellum here called the tentorium cerebelli. It's one of your meninges, the dura, and it extends and kind of covers below here. And what happens is this uncus, if you've got a lot of swelling in your brain, or and you don't have any more space, and the brain gets pushed down, and that uncus goes right over the edge of this tentorium cerebelli and slips over the edge, and it pushes on the oculomotor nerve. And when you push on the oculomotor nerve, your pupil dilates. You have an unbalanced, your sympathetic nervous system dilate your pupil, your parasympathetic constricts. You take away the parasympathetic component, so you've got this dilated or blown out pupil because you're putting pressure on the oculomotor nerve. So that's why the uncus is what we call it. So what happens is, this is the tentorium cerebelli. It's hard. We'll show you this in a sagittal view in a little bit, probably tomorrow. If you have a lesion or swelling or a big, bleed or trauma to the brain above the tentorium, it's called a supratentorial lesion. If you have damage there, if that's bad, if you notice the pupil's blown out, because you're getting so much pressure above the tentorium that some structures of the brain are being pushed down into the tentorium, into that space. Infant tentorial lesions, or lesions that are below, that's like brainstem and cerebellar damage, which are very critical too, because that's your basic breathing and vital functions are in the brainstem area. So anyway. And don't worry about anterior, posterior perforated substances. You can see in here, remember that mammillary body we told you that we sometimes get confused with the optic chiasm or the anterior white commissure, the inflammatory lesion? They're right here, mammillary bodies. Okay, this is sort of the cleavage of the the pons or the midbrain. It's the mammillary bodies. That's why they call it that. Okay. Okay, we got 5 more minutes. Let's just do brainstem real quick. Now we're just going to focus on brainstem, looking at the front part, the ventral part, or the front part of the brainstem. 3 main parts. Here it is. There's the midbrain. Okay. It's been cut off from your brain up here. Okay. Pons. And this front part of the pons is the basilar pons, that rounded front part of the pons, the basilar pons. Medulla, or sometimes referred to as the medulla oblongata. Okay, we typically don't say the oblongata. I just say what's the movie? There's a movie called. Have you heard? Is there a Waterboy? But I'm thinking of Gross Anatomy. There's a movie called Gross Anatomy, which is a whole. You guys need to watch that. It's probably on Netflix. It's really pretty. It'd be a great movie to watch your first year in PT school. It's like with Matthew Modine. I don't know if you remember. Jeez. Anyway, but they've got this anatomy instructor, and he's like, the medulla oblongata, it just makes a big dramatic thing. It's pretty good. You need to watch it. Also, that's one, and then before you go to your first clinical, you got to watch the very first episode of Scrubs. That's a really good one about going out in your first clinical and the experience, and it's very true. It's scary, but true. Other things on the front part of the brainstem, this ventral surface, the cerebral peduncles, that's these. Remember the connecting stalks? The front part, if you look at the very front part of the brainstem or midbrain, that's called the cerebral peduncles. If I say, what is this? And I tag it or identify this structure from that ventral surface, that surface structure, it's a cerebral peduncle. It's that connecting. There's white matter, there's axons running through there to connect you to your cerebrum, the cerebral peduncles, which are part of your midbrain. It's a midbrain structure. Other terms are also, it's also called the crus cerebri, or it's also called the basis pedunculi. It's the peduncles at the base of your brain, the basis pedunculi. It's also called the crus cerebri. So again, there's 3 terms that you might see right across the literature, but most people call it the cerebral peduncles. This area here, this hole, is the interpeduncular fossa. There's our mammillary bodies again. Basilar pons is the front part right here. Then there's a little groove right here. It's very shallow, but that's the basilar groove, and the basilar artery runs inside of that basilar groove. It actually lays on top of it, I should say, the basilar artery. When we get to the circulation, you'll see that. The olives. Down in the medulla, there's these bumps right here and right here called the olives. And when we get to cerebellar function, there's some certain fibers that originate there and go up into the cerebellum. So it plays a role in some coordination, okay? So cerebellar, these have some fibers that go up and into the cerebellum, okay? Then we have in the front part of the medulla here is the pyramids. Medullary pyramids right here. So on each side we have this kind of a triangular shaped pyramidal structure called the pyramids. That's where your motor tracks are running. As they come down from your brain into the brain stem and the front part of the pons, then they run down the front part of the medulla in the pyramids, okay? Just deep to that, you know, as these axons that are motor pathways going down to your spinal cord, okay? And we know that, some of you may know, that with the left side of your brain, motor controls the right side of your body. So they're contralateral pathways, so somewhere they have to cross. And they cross in what's called the pyramidal decussation. Typically you see that in a horizontal section. You see the actual, most of the crossing through a horizontal section, but you can kind of see it in here. It's actually right in this area here. So if you have a little brain stem and you take a probe, you know, a little probe, and you stick it in this ventromedian sulcus right here, this little sulcus here, and you start dragging your probe down, you'll eventually hit a spot where it kind of stops. That's where the pyramidal decussation and those fibers start crossing to go to the opposite side of the body, okay? So that's the pyramidal decussation. So I do have a few brain stems. I need to get some more. I need to take some brains out just to get some better brain stem specimens. But I hate it because you got to waste, basically, you just got to tear apart the cerebrum. Like sometimes I want to get a good brain stem that has like the thalamus is still on it, so you kind of have, you know, up here you'll have some thalami sitting on top right there. It's kind of a nice structure, but we'll probably have to kind of dig around the brain to get all those things. This is just showing you, you don't need to memorize these yet, but all the little yellow guys coming out here, those are all the cranial nerves, okay? So you have, including these, you know, you have your olfactory tract and bulbs and your optic nerve, but you also have all the rest of these yellow things coming out on each side, paired cranial nerves, 12 total, okay? I think we'll stop at this point. Any questions? Doing all right? All right.
Previous slide, that will not be on the quiz tomorrow.
The only thing that will be on the quiz will be just either a medial or lateral view of a cerebrum. Line drawing. So yeah, no brains. Well, you could be asked to identify midbrain, pons, or medulla from a medial view. Okay, so that's all you got to worry about for tomorrow. That's enough for tomorrow. All right, 8 o'clock tomorrow, right? Yeah, good times.